Hello everyone. Today we are going to start our new topic, that is thermodynamic concept of energy. It's one of the most important topic from exam point of view as well as from concept point of view. In thermodynamics we see almost everything through the perspective of system. Here also things are not different. Through the perspective of system we can divide energy into two different ways. First one, stored energy, and second one, energy in transit. Let's see what is energy or stored energy. So we are talking about stored energy. As the name indicates, it is the energy possessing by the system. That means this sort of energy can be stored inside the system. Let's take an example. Here I am having a water bottle. Okay. Now we want to do some experiment on the water which is there, maybe heating it or doing something. I want to study it. So this is my system, right? Okay. Now all forms of energy associated with this system is called the total stored energy. Say when this system is in rest, it will be having some distance from the ground, right? Because of that it will be having certain potential energy. If it is moving, it will be having certain kinetic energy. If we zoom into the microscopic level or into the molecular level, we will see that molecules are in random motion. That is because they are also having some sort of energy. This motion will be there irrespective of whether the system is moving or not. So there is definitely a certain different type of energies associated with these molecules. All forms of energy associated with these molecules are called internal energy. These energies include kinetic energy of the molecules, potential energy between these two molecules, translation energy, vibrational energy, and so on. All together we will call them as internal energy. So if you denote the total stored energy as E, E will be the sum of potential energy that we are already seeing, kinetic energy and internal energy. In thermodynamics, we are not interested in finding the absolute or actual total stored energy of the system. We are more interested in what will be the change during a process. During a process, what is the change? That means final minus initial. We are not interested in what is the initial or final value. Fine. So let's take the change or the change in total stored energy. That is nothing but delta E. Delta E will be sum of change in kinetic energy, change in potential energy, change in internal energy. Now you can see that most of the time or generally, in general, when I am doing some experiment on my system, likewise when we are doing the experiment on my water bottle, it will be stationary. Alright. As a result, its initial and final potential energies are same. So what is the change? 0. Same goes for my kinetic energy also. Change in kinetic energy will be 0. So finally I will be getting that change in total stored energy is equal to change in internal energy, provided I can neglect change in kinetic energies and potential energies. That was pretty straightforward. Let's move on to the next, that is energy in transit, which is very important from a thermodynamic student's perspective. Let's understand that. In the case of total stored energy, we are seeing that these are the energy which can store inside the system. What do you mean by energy in transit? These are all nothing but energy interaction between system and surrounding. This sort of energy cannot be stored inside the system. There are two types of energy in transit, work transfer and heat transfer. Let's see what is work transfer. Fine. Thermodynamically, work is said to be done by the system if the total effect external to the system can be equated to lifting of weight. I'll repeat. Thermodynamic work is said to be done by the system if total effect external to the system can be equated to lifting of weight. We will understand this through an example. Consider that here I am having a battery which is connected to a motor. Motor in turn is connected to a fan. Fine. Now battery as well as my motor is inside my system. That means inside my boundary. That also you can see. Now my question is this: is there any work transfer or not? Just now we have seen that if I can equate the effect to lifting of weight, I can say that there is work transfer, right? Do you see any lifting of weight here? There may not be actual lifting of weight, but through a thought experiment, we can replace the fan with a pulley in turn connected to a rope is connected to a mast. So when the motor rotates, the lift getting lifted up, right? So only thing is that if I am equate the effect to lifting of weight, we can say that there is work transfer. So in this case, there is work transfer. Let's take the same example but with a slight change. Alright. In this case, I am having motor, battery as well as fan. Everything inside my boundary. Everything is there. Now you know that when it is switched on, the fan will rotate, and I can replace or I can equate the effective lifting of weight also. Now my question is that, is there any work transfer is there or not? In this case, there is no work transfer. Because see, work transfer means one place to other place, right? In our thermodynamic perspective, it is from either to system to surrounding or surrounding to system. In this case, is there any transfer is happening? No, because everything is inside the system. Even though we can equate the effective lifting of weight, but it is not crossing the boundary. Fine. So you have to understand that work transfer is a boundary phenomena. Unless and until it is not crossing the boundary, we cannot recognize work transfer, or matter of fact, we cannot recognize heat transfer also if it is not crossing the boundary. That we will see later, but I am just telling you now. Now, so we have seen that work transfer is a boundary phenomena, right? Let's take the same example. Now I am redrawing the boundary again. This time only motor, not motor, battery is inside my system or inside my boundary. What do you say? Is there any work transfer or not? If you compare this with our definition, that means if I can equate the effective lifting of weight, here the same thing is happening and it is outside of the boundary, that means I can say that there is work transfer is there. But still there is some disturbance is there. What is it? You are not completely digesting it, right? Now there are some differences there. In earlier case, the first case, one shaft was crossing the boundary, right? So we will say that there was a mechanical work. In this case, if you look at the boundary, let me tell you one thing. If at all, if you want, there was a problem to see whether there is a heat transfer or work transfer, the first thing you have to see is that look at the boundary. What is happening at the boundary? Here also look at the boundary. If you look at the boundary, you can see that two wires are crossing the boundary. What is happening through these wires? Electrons are flowing, right? How these electrons are flowing? Because of the potential difference created by the battery. This is nothing but electrical work. So you just have to see, look at the boundary. If the electrons are flowing through the wires, through the boundary, then we can say that there is work transfer. This particular work transfer is called electrical work. Later in the class, we will do some of the problems which involves electrical work. Okay? At that time, you will have a better clarity on this. Fine. Now, we have seen what is the definition, how it is working, how we can consider work transfer is there or not, and so on. Now it's time to formulate a equation for finding the work transfer. From mechanics, we have work transfer is equal to force into distance. That means if I am having object, if I am pushing that object with a force F, and if it is moving in a distance dx, then work transfer is given by force into distance. In thermodynamics, we don't deal with the terms like force and distances, right? We have to convert that into the terms like pressure, temperature, volume, like that. So let's do that. For that purpose, let's consider piston cylinder assembly. Okay? When I am supplying heat, you know that the gas will expand, as a result piston will go up, right? So consider the initial condition. Initial condition is there. So internal pressure is acting against the piston. Pressure is equal to the normal force per unit area, right? P is equal to F by A. So F can be written as P into A. When I am supplying heat, the piston goes up through a distance dx. So I can write work transfer is equal to F dx. Instead of that, instead of F, I will be writing PA and into dx. What is this A into dx? A is nothing but the cross-sectional area of the piston into dx. That is nothing but the change in volume. So we will be getting the work transfer is equal to P into dV. This work transfer was for a small distance. If I want to calculate entire work transfer, I will be integrating this from state 1 to state 2. So work transfer is equal to integral P dV. Correct? For any equation, there will be some underlying assumption. Here also there is assumption. Without knowing the assumption, there is meaningless to knowing the equation. So let's understand what is the assumption behind it. When we consider this, we consider that the process should be reversible. Okay, process should be reversible. I will tell you why it is. For example, there is friction between piston and cylinder, and when I am supplying heat, the piston moves up. Okay, according to the condition, I applied equation integral P dV. Say I am getting the answer as 10 units. When I am applying the equation integral P dV, I am getting the answer as 10 units. But if you look at the real case, I won't be getting 10 units outside. Why? because there is friction between piston and surrounding, that means piston and cylinder. As a result, there will be some units of work is utilized for overcoming the friction. So output I will be getting only 7 units, but from the equation I am getting 10 units. Both are not matching, right? So it is very important to know that integral PdV, work is equal to integral PdV, can be applied only for a reversible process. Fine. The next assumption is that we are talking about closed system. So integral PdV is applicable only for closed system process. Fine. Now you know that work transfer can happen from system to surrounding or surrounding to system. If the piston is going up, I will say that work is done by the system against surrounding. If the piston is going down, that means I am pressing it down, that means surrounding is doing work on the system. So both are having different direction. So in order to account this direction, we will follow a sign convention. Work done by the system will be taken as positive, work done on the system, that means work done by the surrounding, will be taken as negative. Throughout this course, we will be following this sign convention. In mathematics, if there is a graph, xy graph is there, there is a curve, then area under that curve is given by y into dx. That is from mathematics, that is from calculus, that is the basis of our calculus. We will divide entire area under that curve into small rectangles, and we will find the area of these rectangles and sum it up. That is how the calculus works. So you know that area under curve is given by y into dx. You know that a process can be represented in a PV diagram, right? So now I am having a PV diagram here, a curve is there. Now area under that curve is given by P into dV, and the total area is nothing but integral P dV, or sum of all the areas, that is integral P dV. We heard this P dV somewhere else, right? Just before some time we have seen that work transfer, that is reversible work transfer in a closed system, is given by integral P dV. That is exactly matching with area under PV diagram. So we can conclude that area under PV diagram projected on volume axis is nothing but reversible work transfer on a closed system. It is very important. Area under PV diagram projected on volume axis is nothing but reversible work transfer in a closed system. Interesting, right? Story is not yet over. Let's continue. Now we are seeing one process, 1A2. During that process, we got what is work transfer. Now let's do the same process. I mean, from state, let's go from state 1 to state 2 through another path. Let it be 1B2. Let me ask you a question. What is a change in volume for 1A2? Nothing but V2 minus V1, right? What is a change in pressure for 1A2? P2 minus P1. If I ask for the temperature, it's same. Change in temperature is nothing but T2 minus T1. Let me ask you another question. What is a change in pressure for 1B2? Same, right? P2 minus P1. Even though the paths are different, since endpoints are same, the change in pressure will be same. That is for the properties. For properties are nothing but it depends only on the endpoints. It does not depend on how the path is going. Fine. So all the properties are changes are depending only on initial and final points. Now let's come back to the work transfer. That's what we are discussing, right? For 1A2, you know that work transfer is nothing but area under that curve. For 1B2, even though the endpoints are same, since path is different, you can see that the work transfer is area under that path. For 1B2, you will see that work transfer is different than from that of for 1A2. That means even though the endpoints are same, when the paths are changed, work transfer is changing, right? That is, work transfer is a path function. Work transfer is a path function. Okay, interesting, right? So in conjunction to it, we can talk about exact differential. All properties are called exact differential. That means irrespective of the path, we can write change in volume as V2 minus V1, change in pressure as P2 minus P1. So we can write all the property changes are dP, dV, dt like that. But can I write dW is equal to W2 minus W1? That means according to context, it will be like work transfer after the process minus work transfer before the process. It is meaningless to say work transfer before and after the process, right? Work transfer will be coming into the picture only during the process. So we cannot write dW is equal to W2 minus W1. It is meaningless. So we will be writing dW as d cross W. Again, work transfer will be represented, you know that it is represented by the letter W. In this case, we will be representing through D cross W. Both are same. The term W as well as D cross W are representing the same work transfer. But only one thing is that work transfer is a inexact differential. So far we have seen certain things about work transfer. That is, starting from work transfer is a boundary phenomenon, work transfer is inexact differential, work transfer is path function, work transfer is not the part of the system. A system cannot possess the work transfer. These are very important points regarding work transfer. Work transfer for various closed system processes. Let's start with constant volume process. Consider that we are having a rigid vessel, and if I am supplying heat in the form of Bunsen burner or something, you know that the gas inside the rigid volume will not be able to expand, right? Because it is inside a rigid vessel. So this sort of process we can say it as a constant volume process. So let's find out the work transfer in a constant volume process. We know that work transfer is nothing but integral PdV. Since it's a constant volume process, what will be the value for dV? Change in volume? 0, right? It's a constant volume. So change in volume will be 0. So I will be getting work transfer is equal to 0. Now let me show you a scenario. Here I am having a closed system, a rigid vessel, and there is a shaft going through it, and a paddle wheel is rotating inside the system with the help of a motor. Now the question is there any work transfer inside the system? Is there any work transfer from surrounding to system or system to surrounding? Let me make it clear. Is there any work transfer from surrounding to system in a constant volume system? Just now we have seen that in a constant volume system work transfer is 0, right? So here work transfer must be 0? No. The work transfer is equal to, the W is equal to integral PdV is for displacement work. That means expansion work or boundary work. There are so many other forms of work transfer is there. In this case, in a constant volume process, the expansion work is 0, but other forms of work can be there. In this case, a shaft is crossing the boundary, so mechanical work is happening. So in a constant volume process, only expansion work will be 0. Other forms of work can be present in a constant volume process. Remember that. Sometimes I have seen that student will be thinking that in a constant volume process, work transfer is 0. So whatever the work transfer is there, they will neglect that. That is not the right approach. Next is constant pressure process. Here I am having a piston cylinder assembly, okay, and there is no friction between piston and cylinder. In this case, I can say that the process will execute a constant pressure process. Let's see how I am saying that. If I am drawing the free body diagram of the piston, I can conclude that. So I am having a free body line is there that is representing the piston. What are the forces acting on that piston? Internal pressure is acting up, right, in the form of pressure force. So that is nothing but P0 or Pi. Let me take the internal pressure as Pi. So the internal force acting upward is nothing but Pi into area. Is there any other force? Piston weight is acting down, right? So that is W, acting down. Now what else? Is there any other force acting on it? Yes, atmospheric pressure is acting on us. See, even on my head, a huge pressure is acting. 1 bar pressure is there, atmospheric pressure. So here also pressure P0, that is atmospheric pressure, into area is acting down. Correct? So I can equate that Pi into A is equal to W plus P0 into A. Correct? Now think that I am supplying heat. When I am supplying heat, you know that the piston will go up, right? Or system is losing the heat, then piston will go down. Whatever any of these process happens, will the atmospheric pressure change? No, right? Will the weight of the piston change? That means all the right hand side is not changing. Then will the left hand side will change? No, right? That means if there is no friction between piston and cylinder, then we can consider that process to be a constant pressure process. While doing problem, we will be encountering this many number of times. So remember these things. So let's find the work transfer in a constant pressure process. We know that work transfer is equal to integral PdV. Since we are talking about a constant pressure process, pressure is constant, we can take it out. So P into integral dV, that is nothing but V2 minus V1. So our transfer in a constant pressure process is given by P into V2 minus V1. Let me ask you one thing. How can I represent a constant volume process in a PV diagram? A horizontal line or vertical line? Constant volume process will be vertical line, right? And what about constant pressure process? It will be a horizontal line. Remember that. That's about constant pressure process. Let's move on to important process, that is isothermal process. What do you mean by isothermal process? A process where temperature remains throughout the process is called isothermal process. Alright, let's find out the work transfer in that case. Before that, let me ask you a question. Can I have a heat transfer in an isothermal process? You may be having a feeling that if the temperature, if there is no heat transfer or if the temperature has to remain same, there should not be any heat transfer at all. Right? Let's see that. Here I am having a piston cylinder assembly, and on top of which a weight is there which is divided into so many small parts. I am going to do a isothermal process with supplying heat. Let's see that. I will apply a small quantity of heat. As a result, temperature will increase, right? Then I will take one small weight away. As a result, the gas will expand. When the gas expands, temperature drops back to same initial temperature. Again, I will supply some heat. Again, slight increase in temperature will be there. I will take one more weight. Gas expands. As a result, temperature decreases back to same initial temperature. We will do this slowly and by taking infinite amount of time. As a result, we will reach from state 1 to state 2 by keeping the temperature same. At the same time, there was heat transfer also. Interesting, right? Isothermal process generally will take a long time. Okay, here also we have seen that we have to take the small amount of weight for infinite amount of time, then only we can achieve isothermal process. Let's find the work transfer in isothermal process. We know that work transfer in a process is given by integral PdV, right? If you are taking an ideal gas, we know that PV equal to mRT. We are talking about closed system, so M remains constant. R is characteristic gas constant, that is obviously constant. We are talking about isothermal process, so T is also constant. So we can write PV is equal to constant, or P is nothing but C by V. If I apply C by V in the place of PdV equation, we will be getting W is equal to C by V into integral C by V into dV. C I will take it out, I will be having integral dV by V. What is integral dV by V? Ln V, right? That is from state 1 to state 2. So by solving that, we will be getting C into ln of V2 by V1. What is C now? C is nothing but mRT, which is also equal to P1 V1. In the isothermal process, P1 V1 is equal to P2 V2. So this C can take any value P1 V1 or P2 V2 or mRT. And in an isothermal process, P2 by P1 is nothing but V1 by V2. So here V2 by V1 is there, that I can replace with V1 by V2. So for isothermal process, we can have set of equation for work transfer that you can find here. Next is adiabatic process. What is an adiabatic process? Adiabatic process is a process where heat transfer is zero. There is no heat transfer between system and surrounding. So a reversible adiabatic process, I will be having equation like PV raised to gamma. It is represented by equation PV raised to gamma is constant. A reversible adiabatic process will follow this equation. Similarly, they are having equation connecting pressure and temperature and volume and temperature also. I am listing out that here. That is T1 V1 raised to gamma minus 1 is equal to T2 V2 raised to gamma minus 1. Similarly, P2 by P1 is equal to T2 by T1 whole raised to gamma by gamma minus 1. So we want to find the work transfer, right? Work transfer is nothing but integral PdV. So in case of P, I can write that C by V raised to gamma, because for adiabatic process, PV raised to gamma is constant. So I will write C by V raised to gamma in case of P, in place of P, and I will be getting W is equal to C by V raised to gamma into dV from state 1 to state 2. Alright. Now if you integrate this and following the steps, you will get the answer as W is equal to P1 V1 minus P2 V2 by gamma minus 1. Next is polytropic process. Polytropic process follows a certain law that PV raised to N is constant. In a polytropic process, there can be work transfer, there can be heat transfer also. Alright, so it just follows that PV raised to N is constant. Only thing is, generally this N value is between 1 and gamma value of that gas. So for that we can get that work transfer is equal to P1 V1 minus P2 V2 by N minus 1. The derivation will be exactly same as that we followed it for adiabatic process.